What a great talk. Excited about this next one. We have a co-founder of Kakarot, Elias Tazartes, giving a talk on speedrunning Ethereum as a ZK-L1. It's going to be a good one. Please give it up for Elias.
Thank you. All right. Hey guys, my name is Elias. I am one of the co-founders of Kakarot. And we've been working a lot on making Ethereum provable. Friday, we became one of the new Beam chain client teams to try and implement a provable Ethereum. Who here has heard of the Beam chain by a show of hand? Okay, not so many. So it's the effort made by the Ethereum Foundation to incorporate more snarks and starks directly into Ethereum. And why does it matter? It matters because in the last few months in crypto in general, we have seen that as a general community, we want more bandwidth and less latency. So we want more execution on Ethereum L1, but we also want more execution on every chain. So Ethereum L1 today does 30 transactions per second. And if you include all the rollups, you maybe get to 300. This is still not enough to scale to the next level, be it the 4,000 sustained of Solana or even the up to 60K of Visa. So we want to grow this. And Ethereum, the core value of Ethereum is not speed. It is verifiability, inclusiveness, security. And so as a result, you have the system POS and also the current execution layer, which assumes small compute and small bandwidth for both the actor that is supposed to propose the block, but also the actors that are supposed to re-execute the block, verify everything is correct, and sign on it. And tomorrow, with the many efforts that are done in the ZK research, you assume that attesters now are even less, have even less compute, but that's fine. And you assume the proposer has extremely large compute. And why are you allowed to do this is thanks to ZK. Thanks to ZK, you can create this asymmetry between an actor that we call prover, that is going to do a lot of work to convince a verifier that something was done correctly. And this is extremely convenient for Ethereum that has already kind of dipped its toe into the separation between builders and proposers. Does that ring a bell? Does that remind you of PBS, the proposer-builder separation? This is one step further, and it's called APS, attester-proposer separation, for those who want to look into it. But it's truly enabled by ZK, because with ZK you can unconstrain the block builder. They can have a huge computer. It doesn't hurt verifiability, which is the core value of Ethereum, because the big builder, supercomputer, is going to generate ZK proofs, certificates of execution for every single block they build. All right, so what does it look like? You have a slot, 12 seconds. You build a block, so you include 100 to 150, maybe 200 transactions in your block, be they trades, swaps, anything, you name it, games, NFTs. And you broadcast your block to the peer-to-peer network. And tomorrow, instead of broadcasting the block, the full block, what you're going to broadcast is a proof that the block was executed with integrity and the sufficient data to verify this proof. So that means that we have a new frontier for ZK to cross. And that frontier is called real-time proving. So I'm sure you guys know, who here has heard of the concept of ZK rollup? Yes, so everyone. So ZK rollups create blocks. They create zero-knowledge proofs of those blocks, and they submit those proofs to Ethereum L1. They're not so constrained by time just yet, which means that they have minutes, if not hours, to generate those proofs. So today, let's take Starknet example. It's a zero-knowledge rollup. It takes up to 8 hours to settle proofs on Ethereum. Of course, it's for matters of aggregation, but that's not the question. It means that today we need to cross a new kind of 40x in speed in proof generation time to be able to claim that we can make Ethereum a ZK-L1. And for that, it means that kind of as engineers and the researchers, we need to really zoom in into the proof lifetime, find every single bottleneck or every single second that we can gain, and do it. And that's this diagram showing you that as soon as the proposer creates a new block, you need to pre-process the block to create prover inputs. You need to generate a so-called trace. And then you can generate your zero-knowledge proof with that trace. So there are essentially 3 main steps. You can add 1 or 2 depending on who you are and what you're doing, proof wrapping, proof conversion, but let's focus on those 3. And the point of today is to say, a block, that way you can have the orders of magnitude in your head. So a block amounts to, let's say in the hundreds of millions of so-called cycles. You can use them as arbitrary unit. They're the CPU cycles for ZK-VMs. So between 250, you can go up to 600 million, sometimes 1 billion, depending on how big the block is. And so we use this speed measurement, hertz. So megahertz is 1 million cycles per second. So TLDR is, you will see in the benchmarks, if you look a bit into it, the megahertz word come up a lot, and the cycle. So I just wanted to give you this mental model. We are at the 10 of megahertz order of magnitude, and a normal CPU that you have in your computer is rather at the order of magnitude of gigahertz. So you have this 1000x that you need to reach to be at the same speed as CPUs, but we will be fine with 100 megahertz for now, and until the next years. So let's just dive into it and see where time is spent. And if you want to follow more closely this effort, there's a website called ethproof.org. I'll come back to it, but this is where all the data on proving Ethereum is aggregated. And I have 8 minutes. OK, cool. So as I said, generate proof inputs, generate trace, generate Stark, broadcast Stark. I'm using the word Stark. You might have heard the word Snark. They are similar concepts. It's just that everyone is using Stark today, most people. OK, so we called it ZK-Pig. You can call it anything you want, but it's a ZK prover input generator. And what you do is you essentially take a block, and you take the entire state of Ethereum, which is in the terabytes. And of course, you can't send that over the wire. And you try to go to the substrate, the exact minimum state that you need to run this block without having access to a database in real time. So what that means is that if my block has 20 transfers from me to all you guys, the prover will need my balance at the beginning of the block and all your balances at the beginning of the block, and no one else's. So this is what we call the kind of pre-processing, because you need to extract the absolute minimum needed to execute your block. And that goes for the code that you touch, the storage that you touch, and so on and so forth. And there are many tools to do it. There's one by ReZero, one by Succinct. I think they're similar, one by us. At the end of the day, it is something that should not be your problem because it's mostly engineering, it's not ZK. And so today, with a remote RPC, we already have a problem. We're at 2 minutes to generate those inputs. So the obvious endgame, which is simply a matter of optimization, you need to run this step as you construct the block. We're already seeing that we're already out of our 12-second deadline. So we need to optimize this in the next month or 2. So OK, let's say our slot is 12 seconds, and we only allow the prover input generation, which is just pre-processing, to take up to 1 second. And ideally, you want it to take 0 seconds. And today, it's 2 minutes if you use a remote RPC to query all of the storage that your block is going to touch. And the time that you see is mostly just ping, round-town ping, because you have to ping remote RPC every time you hit a storage slot. All right, so let's get to a more interesting part, generation trace. So trace, you have to think about it, this is my mental model. You have to think about it as this big Excel table, where every single row is the state of your computer, your virtual computer, the state at every step. So first step, I'm initiating my program. Second step, I've done some things. And every row of your Excel sheet, you're logging the exact state of your computer. And this is going to be useful because the prover is going to do nothing else than check that every single step respects the constraints of the way your computer is supposed to work. So what do you want to prove? You simply want to prove that a program, which is the Ethereum execution layer specification, the EVM, the Ethereum smart contract execution engine, is operating correctly so that it runs on inputs, the current state of the world and the block, and produces some output. And this, I think many of you have heard it. It is colloquially, scientifically named the state transition function. So the only thing you need to prove when you're proving Ethereum execution is proving that the state transition was done with integrity. And this is what validators do every day, all the time. The only difference is that they do this by re-executing the entire block, block after block. So every time a new block is produced, you expect all of the nodes to re-execute transactions. What ZK does is that you now expect people to verify proofs, and the main difference is that proofs are exponentially cheaper to verify than a re-execution. So that's it, block data, Ethereum execution layer in a ZK environment, and that gives you a trace. And just to give you our lessons learned at Kakarot, the thing we did was have a ZK native implementation of the Ethereum execution layer in Cairo, and that gave us the ability to run blocks in a provable environment, which is the Cairo VM. All right, so how fast is this, and is it a bottleneck? I phoned our friends at ReZero and asked them, what is the theoretical max that you have right now to generate a trace for a chunky block? Let's say block 21 million. And they gave us 5 seconds for that block, which is not too bad, but maybe a bit problematic for the real-time element, especially sub-block. And this number is if you have an extremely big CPU, but we'll take it, and we think that the space is pretty much well advanced on this. So we have 10, maybe 5 seconds, depending on the block, for trace generation. And if your block is too big, you are already out of the game. You are above your 12 seconds, and that's a big problem. So I think the key idea is now people are looking into parallel trace generation. I guess parallelization is the obvious answer that most people throw at many problems in engineering, and that's what we are doing and most teams are doing. The other thing you can do is break a block into chunks, but that also gives you heuristically parallelization. OK, so now generating a Stark. So as I said, you have this trace, which is a big Excel sheet, and then you have a Stark prover. So I have this very high-level, very dumbed-down version of a prover. Disclaimer, I'm not a cryptographer myself. I'm a zero-knowledge engineer. But this is how I view a trace, simply that every row in your table is a state of the CPU at a particular moment, and what you're going to apply on it is polynomial constraints. This is really, I think this helped me unlock kind of a better understanding when the word traces or Starks are thrown out. So this is now how I see it in my non-cryptographer brain. And so this is very simple. You feed to your provable computer the EVM specification, so the way you expect EVM to work. You feed it the inputs, and then you generate a Stark. And the goal is that this Stark is extremely portable. You can send it around. And for those who have been to some Celestia events, this is what unlocks proof-based interop. If you've been to some succinct events, this is what unlocks verifiable servers. This is at the heart of everything we do, which is verifiable computing. I think that's pretty cool that we're building towards including it directly in the core of Ethereum L1, not just rollups. OK, so today, if you go on ethproof.org, which is the website in which, where all the provers, 16, ReZero, us, Narcify, ZK-EVM, many others, are posting proofs of Ethereum L1 blocks, you will see that the average time is in the 2 minutes. So that's already a problem. If you are stacking a lot of GPUs together, you can go down to maybe 30 seconds, but that is very costly. So I think there's a double challenge, which is how can we go to 5 seconds for this, and how can we make it not too expensive? So you ideally don't want to put many GPUs together if they're too expensive. OK, so that's it. And again, you need to heavily parallelize the prover. And I will maybe not talk about it, but hint at it. There are many teams working on hardware acceleration. It seems like a buzzword, but at the end of it, it's just lots of cool GPUs engineers that try to write libraries for provers on the GPU. And the other thing is some low-level optimization, like how can you transfer data from the GPU and CPU fast, and even create new kind of chips, which I think what Fabric is doing with the VPU. OK, once you have it, you just have to propagate it. If you're L1 to attesters, if you're roll-up to aggregation layers, or just L1. That might be a problem, though, because the proof is several megabytes, maybe 1 or 2 if it's a Stark. So there are tricks to make it lighter, but that's not the crux of today. So that's it. We need to get this in under 12 seconds. I think you can expect by end of year, even before, that teams are going to be able to do it. And I'm This is what we're working on every day. Our team, 10 people, mathematicians and engineers in Paris, and the goal is to prove any blockchain. So that's it. Thank you so much.